Hello, good morning, dear, and welcome back. So you have started watching a video on support vector machine training. I believe this is the most interesting part in support vector, and in that context, we will study with some details about a very famous algorithm called SMO algorithm, sequential minimal optimization algorithm. And one good thing about support vector machine dwell problem is, and the constraint is that it is suggesting the KKT dwell complementarity condition is suggesting that out of many samples there will be only handful of support vector, because those samples, only those samples who will be support vector for which the Lagrangian multiplier alpha I is non-zero. Okay, so you just need to see in the iterative process of the algorithm that if they are zero, then they are not support vector, and that condition is telling that. Okay, let us start. Okay, so in training support vector, we are using dual problem, as you know. So our objective function is maximize W. That is, this is not, again I am telling, this is not parameter W. Okay, this is not. This is rather a function, objective function, dual objective function, which is only a function of alpha support vectors. Okay, and what is the nature of the function? Quadratic in nature, because this is one alpha, alpha square. So this is of the nature A alpha square plus B alpha plus C. Okay, so this is the nature of the function. Okay, equals to. Okay, and subject to the constraints are, this is, we are considering soft margin support vector machine. So alpha I will rest between 0 and C is a regularizer term, constant term. Okay, and I equals to 1 to up to M, and this is another constraint which we have got from primal problem. You remember primal problem by differentiating the, which was with respect to B and making it to 0, we got this. Okay, we got this condition. Okay, okay. So these are my raw materials. Okay, for running the algorithm. Say we now have a set of alpha i's that satisfy the condition 8 and 9. Okay, and now say that we want to vary only alpha I, keeping everything is fixed, because as a first choice we will try to try to implement coordinate ascent algorithm, which is very simple, which you have studied in my earlier class. So let us try to implement it. Will it work? Now let us look deeply. So this is a constraint, and I can write because alpha 1 y 1 plus alpha 2 y2 plus blah blah alpha m y m. This can be only, of course, 1 and minus 1. Okay, so this is so these are the alphas. Okay, and this is the constraint that is equals to 0. Now from here, alpha 1 into y prefix 1 equals to, so this is actually alpha 1 y1 plus keeping everything starting from 2 to m, okay, alpha I, y prefix I, okay, equal to 0. And so keeping this here, this will be minus this, okay. So multiply both sides by y1, okay. So what we are going to get, this y1 belongs to only two class, is a sample, is a level, okay. So I have two class, -1 and +1. So square of this level will be 1. So this will be 1. This will be equals to 1, okay, and I have one level minus here, okay. So alpha, there is no iterative way, iterative way that alpha can change its value. Why? Because you see alpha 1 is constant. The moment everything, this alpha I equals to 2 to m for all the samples is constant. This is constant, this is a level, okay. So alpha is exactly determined by other alpha i's which initially whimsically you select, okay, to run the initiate the algorithm. But the moment you select, there is no way that alpha 1 can be changed, okay. The simple expression is telling you that. So that's the reason coordinate ascent algorithm as such cannot be used for training our support vector machine because of the constraint. Otherwise, in many cases, it's a great algorithm for training. So we'll have to look for something else, which is actually SMO algorithm. Okay. So SMO algorithm, what it does, it takes instead of 1, so 1 degrees of freedom we incorporate. So instead of taking only 1 alpha and trying to change its value towards optimization of W, what it is done in case of SMO algorithm, take any 2 alpha values whimsically, okay. And there are of course many heuristics. If when you study the paper, you will see they are very intelligent heuristics to select alphas. But the basic idea is 2 alpha at a time we will select instead of 1. So a pair of alpha I, alpha j can be used using some heuristic. In AI, a lot of heuristics are there. So here the normal sense of using a heuristic function is that select those alphas which make very quick changes, okay, and progress in attending W towards global maxima value, okay. And then reoptimize W, which is a function of alpha, with respect to alpha I and alpha j, holding all other alpha k's, k not equal to I and j, fixed. So that's very simple, exactly similar to what you have seen in coordinate ascent algorithm. Only difference is here there are 2 parameters taken at a time for changing, okay. And then we have we can test the convergence of the algorithm by checking KKT conditions, as we have written down here, okay. So 4, 5 and 6 KKT conditions, okay. And let us try to see that what are the main ideas. Suppose we decide to optimize Wi by varying alpha 1 and alpha 2, keeping all other fixed. So from the constraint equation 9, okay, so that is exactly what again I am telling you got by differentiating with respect to b and making it to 0, that I equals to 1 to m alpha I y I equal to 0. So that's the constraint, okay. So we will use again that constant for finding the values of alpha. So 2 alpha we have taken, say it need not be named as alpha 1 alpha 2, but we have done it. You can for your convenience. So alpha 1 y 1 plus alpha 2 y prefix 2 plus all other constant I equals to 3 to m alpha I y prefix I equals to 0. The constant 9 is telling me that. Okay. So that gives you alpha 1 y1 plus alpha 2 y2 equals to, this is going in that side, minus I equals to 3 to m alpha I y suffix I equals to say zeta. Okay. Now from constraint 8 we know that alpha 1 and alpha 2 must lie within the box constraint. You see here is the constraint 8 that alpha must lie between 0 and C. Okay, we are talking about that box constraint. It has to obey this constraint. Also, to obey box constraint and straight line simultaneously, say within, so this is our box. So we are trying to pictorially show how the algorithm will work. Say this is alpha 1, this is alpha 2, this is my box constraint 0C, 0C. From here to here it is C, from here to here it is a square box. Okay, and this is my constraint. What is that constraint? Constraint number, modified constraint number 9, that is alpha 1. It's a straight line. Okay, straight line. And this constraint, okay, this could be here. Sometimes I do not know, the constraint could be here, could be here. Okay, so those are the that will depend on the iteration and alpha 1, alpha 2. But just simple one case. Suppose this is my constraint. So all my solutions will be lying here. So this is non-feasible zone, that is cancelled. Okay, so how we could still get the alpha 1, alpha 2 values. So here is how it works, right? Now alpha 1, alpha 2 we have selected, alpha 1 plus alpha 2, and then we are progressing, we are optimizing, re-optimizing W alpha, which is a quadratic function, A alpha square plus B alpha plus C of this nature. Okay, and so to do actually that, we need to do a little bit more math here. See, so these are the constraint, box constraint, and if to accommodate that straight line constant also, because the box constant is due to our KKT condition, right? Here SMO algorithm have generated another straight line which is constraint. Okay, so simultaneously we'll have to satisfy both these two, and then say alpha 2 will lie between L and H. Okay, as a matter of fact, this is alpha 2. So alpha 2 will lie between L and H. We will see how it is. So using equation 10, we can write alpha 1 as a function of alpha 2, isn't it? So alpha 1 equals to, same as earlier, that we can multiply both sides by yi and then yi square, making alpha 1 free of yi will be equals to zeta minus alpha 2 y2 times yi. Is it clear? Because here there was another this thing, and we have multiplied both sides, and this y is due to that multiplication. And since there was one y1 multiplied by y1, that made it 1, isn't it? We have discussed that, or not? So y I actually is minus 1 and 1, right? So so here there was one yi, so and then multiplied by, so yi square will be always 1. That's it. Okay. So Now alpha 1 is free, and alpha 1 has been expressed in terms of alpha 2 and some constant, level constant like that. Okay, and zeta are constant because all other you have fixed. Okay, so hence the objective function will look like this. So now so it is a function of one variable only, because now alpha 1 also is gone, it is constrained, it is expressed in terms of alpha 2. So it's a quadratic function of alpha 2. Okay, so these are actually, what are these? These are the W. Okay, these are W alphas, different W alphas. Okay, so as long as W's and you are running gradient descent algorithm like, okay, so you are trying to figure out the optimum point, right? And say as long as those those functions, okay, are lying within this box, there is no problem. So whatever value you are getting, okay, alpha 1 and alpha 2, that's the value you need to keep it, and that optimum value, okay, because those values are together with this straight line are satisfying, and you are reaching this, you are getting all this alpha, this is alpha 1, this is alpha 2, this is alpha 1, this is alpha 2, if your optimization convergence is at that point. Okay, so necessarily you collect those alpha 1, alpha 2 value by running this algorithm. This algorithm you are running. Okay, very simple. However, if by chance that the function for some alpha, because there are 1000 alpha, right, for some 1000 samples, and you are taking two at a time. Suppose you have selected some alphas for that, and you have expressed again out of 2 alpha 1 with respect to other to obey the constraint, and say for that the optimum point is here. Then, so it is violating the box constraint. So what to do? The idea is that you can just clip it, and the nearest logical value of alpha 1, alpha 2 you pick from here. So you cannot, is it clear? You cannot take this alpha 1 value and this as alpha 2 value. Can you? No, because they are violating the box constraint. Okay. So the choice is, and same thing, say you have for some combinations of alpha, your function is here. So again you need to clip to come back to this point. So your alpha 1 will be that value, okay, and alpha 2 will be 0 for this. So the idea is clear, right? So this is what actually box constraint without any the straight line constraint. The moment straight line is coming over here, and the straight lines can actually be anywhere, here, as I showed, that straight line could be here also. So here also, right? So then your H and L will vary accordingly. If it is here, say for some reason this is my, so this will be my H. You follow? If my straight line is here or straight line is here, then this will be my H. L remains same. So between L and H, the box will take the shape between L and H. Okay. I hope this is clear. Okay. Okay. So this is the concept of the basic essence of SMO algorithm. Any question, you come to the discussion forum. And now let us see that how whatever I told, how it can be written in this form. Say alpha to new unclipped. That means you have alpha values here, new value here, unclipped. So if you want to maximize W alpha subject to box constant, then simply you need to use the unclipped value like this. Okay, so new value will be equal to H if alpha to new unclipped greater than H, isn't it? Alpha 2 if greater than H, then you just, because you will have to obey this constraint, box constraint, so you cannot go beyond this. So select, if anything beyond this, you select H. Okay, because now without box constant, this will be, of course, this function, but the moment you are constraining it, your solution will be constrained. Okay, so it's H if it is greater than H. You can keep as it is new and unclipped if alpha 2 new and unclipped is less than equals to H. So we have retained the notations same as the original algorithm, so that it will be easier for you to read the algorithm now. Okay, is it clear? It is very simple. Okay, you see, it will be as it is if it is less than equals to H. That means if any solution is here within this zone, okay, so box constant is within this zone, then it will be as it is, and then it will be L if alpha new and unclipped less than L. Okay, so that's very simple observations which you can make from the figure. Okay, so pictorially we have seen. So it's very simple, right? That box constant is there because of submargin sort vector machine, and you are using two Lagrangian multiplier at a time to optimize W and collecting that pair, okay, optimum values for the pair. And this is the way algorithm runs. And once you get all the alpha i's, okay, then I'll have to calculate W parameter and B from the support vector machine, okay, because then only we'll claim that it has been trained. So how to get them? Again, we'll have to go back to the primal problem, and we know that we have optimized it, okay, primal problem. We have optimized that Lagrangian function with respect to W, making it to 0, and I got this, and now these alphas are known to you. Okay, these samples, training samples are known to you. They are the level of the training samples. So everything is known. W is perfectly known to you. And then knowing W, B can also be figured out. Let us see how to figure out B. Just again recall that primal problem constraint y I W S plus B minus 1 equal to 0 for samples on the garter. So this was the constraint primal problem initial lectures, okay, and say this is my one end of the garter, another end of the garter. So this is negative sample garter, positive sample garter, and in between this is my decision boundary, okay, exactly equidistance between these two, right? That's how the decision boundary will be developed, okay. So here you see again repeating the same thing. We are multiplying both sides by yi, so this square equals to 1 into this, and this becomes B is equals to y prefix I minus W dot Si. Now let us see the negative sample garter, the B. What is B corresponding to negative sample garter? So this garter will be the B So this is B, this is the intersect, right? OA1, OA minus equal to, we are calling B minus, which will be the maximum or the worst case samples, because worst case samples only will be the on this gutter, and they are the support vectors like this and this. Okay, so maximum over I, yi equals to -1. I need to compute this. Is it clear? And then I will get this. Okay. Similarly, this you can also figure out by other. So this is the extreme worst case of the positive class. Okay, this is positive class. Y equals to yi equals to 1, negative class yi equals to -1. So you calculate this by it is minimum over I. Okay, that is worst solution, worst samples. Okay, you calculate again this. Okay, this is positive sample, this is negative sample, and these are support vector lying on the gutter. Okay, that's how you maximum value will have to take, OA minus, OA plus, and then the B optimum will be in between them, that is OA, which is OA minus, OA plus minus OA minus divided by 2, because half A, I told you that this is half A, so that's half. So that's the expression which you can use minimum of this, and SMO algorithm actually is simultaneously calculating B together with W. Beautiful. So at the end, if you give the sample with a level, at the end you will get W and B and corresponding all alphas which are actually with support vector, because all other alphas which are not with the support vector will be 0. So you will get as an output of the algorithm. Okay, and that's it. The machine is trained. You have got from the dual problem running SMO algorithm all alphas, and the moment you got alphas, W is got, and the moment W alpha is known, you are using that classical constraint for samples to be on the gutter to figure out B. Okay. So far so good. The machine is ready. Now how to predict? Again, go back to our original preliminary concept, that what was our decision rule? This is the decision rule. W dot is a dot product Si any vector, okay, plus B. Okay, so this is support vector. Okay, plus B, which is W now is known, is equals to this. Okay, so actually W is now the dot product between support vector for which it is trained and any other sample which you want to test, that in which class it belongs, plus B. So this expression is fully known now. Okay, and so once the training is over, you take any sample, just it will calculate the dot product between support vector and the all the support vectors and that sample, and it will calculate whether the expression is greater than 0. If it is 0, then sample belongs to positive class. If less than 0, belongs to negative class. And this classification is over. And the beauty of support vector machine is, you see, it is elegant. It is making a maximum margin so that your classification, misclassification chances will be minimized. And even if there are some outliers, we have also handled that situation by incorporating additional constraint and keeping some value of C. It could be any value, okay, suitable value, which we will discuss afterwards. So with this, the training process and predicting process of a support vector machine is known to you. And with this, we are coming to the end almost of the lecture. One Major thing is remaining. So far we have assumed that support vector machine is a linear machine, okay, with so much of elegance. It cannot be confined to only separating linear classes. So you are right. We are going to discuss kernel from the next class. Okay. Till then, stay safe and come to the discussion forum if you have any doubt. We'll discuss, and goodbye then.